Hello students, in this video we'll discuss continuous random variables, their probability density function, and their cumulative density function. A random variable x is continuous if x maps a sample space into the real numbers, and there is a function f mapping r into r, real valued, such that the probability that your random variable is in a set B is the integral over that set B of f of x dx. And so the most typical context we see with these problems is we typically see the set B being an interval. So in the case when B is an interval, we see that the probability that x is between A and B will be the integral from A to B of this function f of x dx. And this function f of x is called the probability density function. This function is real valued and it has to have two special properties. So for this probability density function, it's a function from R to R, but in fact it's more restrictive than that. We need two main properties for PDFs. So PDFs, probability density functions, must satisfy two properties. The first property is that f of x is greater than or equal to 0. And the reason that it has to be greater than or equal to 0 is if f of x was ever negative, even on some small interval, I could have a negative probability, right? So this prevents negative probabilities. The second condition we need is that the integral from negative infinity to infinity of f of x dx is equal to 1. And the reason we need this is because if I look at the probability that x is between negative infinity and positive infinity, we know that that probability has to be 1, and that is the integral from negative infinity to infinity of f of x dx. So those two conditions are necessary for a PDF. Then, so we can see a quick example of this. So the function f of x, which is 0 if x is negative, and e to the negative x if x is greater than or equal to 0, is a PDF. And so what we have over here is we can clearly see that, well, x is 0 when x is negative, and e to the negative x is always greater than or equal to 0. So we see that, in fact, this satisfies condition 1 trivially. And now let's integrate this function from negative infinity to infinity and see what we get. Well, between negative infinity and 0, I should get a 0. So all I do is I integrate from 0 to infinity of e to the negative x dx. Now this will be negative e to the negative x from 0 to infinity. And the top limit vanishes and the bottom limit is equal to 1. So I have a negative 1, and that's equal to 1. And so in fact condition 2 is true. So this is a PDF. And later we'll see that this one particular PDF is a special case of an exponential random variable with parameter 1. Now we can define a function f capital of x as the probability that x is less than or equal to x, which is the integral from negative infinity up to x of f of t dt. And this function over here is the conditional density function, the conditional distribution function of the random variable x. And we'll discuss properties of this CDF in the future videos. Thank you very much.